All right, you listeners, welcome back to Circuit Chats. You've learned how diodes work, how they model in circuits, and how they power the simplest rectifier. So now it's time to push forward with something a little bit more powerful to look at the complete diode application. So what's coming up today, we're going to talk about full wave rectifiers. So why waste half your AC wave when you can use both? We're going to go ahead and break down how full wave designs deliver a more efficient DC output. We'll also talk about filters. So once you've rectified the AC, it's still a little bumpy. So filters help smooth things out. And then we're going to look at capacitors, inductors, and more and how they play a role in that. And then we're going to look at an entire voltage regulator. So uh, regulators, what they do is they lock in a consistent output voltage, protecting your circuits from ripple and fluctuation. So we're going to look at the components that make up voltage regulators. And at the end, we're going to get into half-wave rectifier assignment here, where we're going to do a hands-on challenge, solving, sketching, and thinking about a real-world half-wave design. Okay, so if the half-wave rectifier is the training wheels of power supply design, then today's circuit is the performance bike. So meet the full-wave rectifier. And what's a full-wave rectifier? Well, this circuit takes the entire 360 degrees of the AC waveform and turns it into unidirectional current. So instead of tossing out half the input like a half-wave rectifier, full wave rectification makes every part of the wave useful. And so how does that work? So during the positive half cycle, one diode path is conducting, right? And during the negative half cycle, another path flips that negative voltage to positive. And so on that cycle, the other side is also conducting. So the result is that we have a waveform that pulses twice as fast with no gaps in conduction for the output. Now, what's an advantage of this, you ask? Well, I'll tell you. You get an output that's smoother, more efficient, and easier to filter into pure DC because we're taking advantage of both negative and positive cycles. The output frequency will always be twice the input frequency, only because we're cutting the input in half and we're flipping it. So we're going to have double the frequency. So if our AC source was, say, 60 hertz, our output waveform is going to be pulsing at 120. So that means less ripple, less filtering needed, and better performance. What else? We can look at the average output voltage. So V sub average should be equal to 2 times voltage peak divided by pi. So that's twice what you get from a half-wave rectifier for the same peak voltage. And you're probably saying, what's the big deal? Well, you get better power delivery, you get more compact filter design, and this is used in almost every serious power supply design today. This episode, we're diving into the center tapped full wave rectifier. It's a brilliant way to use just two diodes to capture both halves of an AC wave and keep current flowing in one direction. So what's special about this circuit? So this full wave rectifier uses what's called a center tap transformer. This means that the secondary coil has a middle wire that acts as a reference or ground. It creates two outputs that are 180 degrees out of phase. Uh, One from the top half of the coil and the other one from the bottom half of the coil. And this is how it works. So during the positive half cycle, the top end of the transformer becomes positive, and so the associated diode D1 is forward bias, and then that conducts. D2 is reverse bias, and that blocks current, so current flows through the load resistor. Now during the negative half cycle, the bottom end becomes positive, the top becomes negative. So now D2 conducts and D1 blocks. Again, current flows through the load in the same direction as before. And what's the result? Both halves of the input waveform are rectified into pulses flowing in one direction. And that's what makes this a full wave. So what's the role of the center tap? So it splits the transformer output into two equal but opposite voltage swings. So letting each diode handle um, one half of the wave. What else? So yeah, so each diode again only sees half the total secondary voltage. So the new output would be a V output B would be equal to V secondary divided by 2, since we're only looking at half, minus 0.7 volts, which is that barrier voltage. Now again, the peak inverse voltage is still going to be equal to the voltage on the secondary for each diode. And why would we use this particular design? Well, one, it's only two diodes instead of four, and I'll show you one with four in a little bit. It's efficient for moderate power applications, and anything else is it just requires a special transformer with that center tap already built into it. In the last slide, we introduced the center tap full wave rectifier. Now it's time to zoom in and watch it work, starting with the positive half cycle of that AC input. So what's happening right now during the positive half cycle? Here's how current is flowing through the circuit. The top end of the transformer's secondary winding, that becomes positive. The center tap is ground, so the upper half of the coil is forward bias. This turns on D1, so D1 is on, it's conducting. It allows current to flow from the transformer through D1, through the load resistor, and back to the center tap. Now on the other diode, D2 at this particular point is reverse bias at this time. So the bottom half of the transformer is negative, so D2 blocks current completely. And so only D1 is active, and it's the only thing that's conducting, so it pushes current in the correct direction. Again, what about the output? Just like in the half wave rectifier, you get a positive pulse across the load, but this is only half of the full wave cycle. The second half is coming up next when D2 steps in. So each diode handles one half cycle, but the output current always flows in the same direction through the load, and that's the secret behind this full wave rectification. Okay, so we just finished following current through the positive half cycle of a center tapped full wave rectifier. Let's see what happens during the negative half cycle when the AC input just flips. So here's what's going to change. The bottom half of the transformer's secondary becomes positive, while the top becomes negative. That flips the biasing across the diode. So now D1 is going to be reverse biased, meaning it's off, and D2 is going to be forward biased, meaning it's on. The current path, so current flows from the bottom half of the transformer through diode D2, which is now conducting through the load resistor R sub L. And again, it's going in the same direction as before, and back up through the center tap to complete the circuit. So the output waveform, even though the transformer voltage switched polarity, the current through the load didn't actually reverse. It's still going in the same direction. So your V sub out um, always stays positive. And now you get a pulse for every half cycle of the input. So that's the power of the full wave rectification. Both halves of the AC wave are used. Output pulses come twice per cycle now, so the frequency doubles. And then diodes take turns conducting, and the result is you just get a smoother DC out of this type of circuit. So far, we've traced current flow through every part of the center tap full wave rectifier, but so let's go ahead and break down the numbers, specifically the peak output voltage and the peak inverse voltage rating for your diodes. So let's look at the peak output voltage. So when you're using a center tap transformer, the total secondary voltage is split in half, so one half for each diode. So if you remember that, we're using practical diodes, which means we're going to have to take into account the 0.7 volts when those are forward biased. So then we have this equation for determining V out, right? So voltage P out is going to be equal to voltage P in the secondary divided by 2, because we're cutting it in half, that minus the 0.7 volts, and that's our formula. So let's say if the total secondary voltage is 30 volts peak, that means each diode's only going to see 15 volts. If we subtract 0.7 volts from that 15 volts, we're left with 14.3 volts for the output peak across the load. Again, this is in forward bias. What about the inverse voltage, peak inverse voltage? So remember, the PIV is the maximum reverse voltage each diode must be able to block during its off half cycle. And we always want to rate these, get them at a rating that's higher than the peak voltage that we have. So if the peak inverse voltage is going to be 2 times VP out, remember we have to add that 0.7 because of the other diode that's in the circuit, right? So again, you're thinking, why? Why that other diode? What does it have to do with anything? Because when one diode conducts, the other sees both halves of the transformer winding plus the conducting diodes drop. So we have to always include that other diodes drop now in the full wave rectification. So we don't have any numbers here yet, but just remember at least 20% or 20 to 25% higher than what your calculated PIV is going to be for your circuit, just for safety. Okay, so we've explored how center tap full wave rectifiers operate. Let's apply what we've learned in a real world example. So say you've got a center tap full wave rectifier. The primary side of the transformer is powered with 100 volts peak AC. The turns ratio is 2 to 1, meaning that the secondary voltage is half of the primary. Let's go ahead and solve for peak output voltage, right? So the and the peak inverse voltage. We're going to look for both of them. But the first step for the peak output voltage is find a secondary voltage. So the transformer we said was 2 to 1. So voltage on the secondary should be the primary divided by 2, which is 100 volts divided by 2, which should give us 50 volts. That's total across the whole secondary winding, right? In a center tap, each of those would get half, so that would be 25 volts for each section for a center tap. Um, Okay, so now we're past the transformer, and we're going to the individual diode. So we're going to apply the diode's forward voltage drop to our equation now. So VP out would be, if we're using a full wave rectifier going through one diode, it would be 25 volts minus the 0.7 volts to forward bias the diode, and that would leave us with a VP out of 24.3 volts. And that would be on the positive cycle. And then it does the same thing on the negative cycle. So next we can look at the peak inverse voltage that the diodes have to handle, right? So PIV is equal to 2 times VP out plus the 0.7 volts, right? So that would be 2 times 24.3 plus 0.7, and that ends up giving us peak inverse voltage of 49.3 volts. And so again, wanting a diode that can handle 1.2% of that, or 20% higher than its rating, we're going to get something that's greater than or equal to 60 volts that can handle that, which is a good margin above that 49.3. All right, so the final answers would be the peak output voltage was 24.3 volts. The required diode peak inverse voltage rating would be 49.3, so we recommend a diode that can handle 60 volts. So now we're going to be building off of everything that we've learned so far, and it's time to introduce a real workhorse of modern power supplies, and this is the bridge full wave rectifier. And again, I know what you're thinking or asking, what is a bridge rectifier? It's a clever circuit. It uses 4 diodes arranged like in a diamond-like structure, the way you see there in the diagram. It does this to create full wave rectification without needing a center tap transformer. So if you didn't have a center tap, this is the way to go. And this is how it works. So starting off with the positive half cycle, when the input AC wave is positive, D1 and D2 are forward biased and conduct. And then the other ones, D3 and D4, those are reverse bias, so they block. So current flows through the load in one direction, just like the center tap rectifier did. And so what's the output? You get a waveform that matches the positive half of the AC cycle every half cycle. So thanks to the diode's switching action. And why is this design so popular? Well, one, it doesn't require a center tap. You can use any transformer. You can use a regular transformer. Uh, Same thing, both halves of the AC are used, so it's full wave efficiency. It's compact and scalable, so this is perfect for small devices and large power systems. So remember that in each half cycle, you have 2 diodes that are conducting. So imagine where we said the positive half cycle where D1 and D2 are forward biased, those are conducting. So we have to account for 2 barrier potentials, so 2.7 volts. Not 2.7 volts, but 2 of the 0.7 volt barrier potentials. So we now have to account for 1.4 volts when any of the pair are forward biased. So VP out would be equal to voltage on the secondary minus 1.4 volts. Okay, so we're going to get to see this one more time, a different, slightly looking different picture. Again, this one just doesn't have the transformer. But let's look inside what's happening in the bridge full wave rectifier to trace current flow during the positive half cycle of the AC input. And that's it. So grab your mental pencil. We're going to follow some arrows. So when the AC input is positive, again, we did this in the last slide, but we're just covering it again with a slightly different picture. Maybe it helps. Okay, the top terminal of this AC source, that becomes positive. The bottom is negative. That means that the forward bias diodes are going to be D1 and D2. D1 and D2 are on if they're forward bias. D1, D2 both allow current to flow into the load, right? And then D2 actually completes the path back to the negative side of the AC supply. So D1 to the load, coming back through D2 back to the AC. And D3 and D4, they're reverse bias, so those are off. They're not even in the circuit. So that's the current path from the AC source positive terminal through D1 into the load resistor out to D2 and back to the AC source, its negative terminal. Now notice that the current through the load always flows in the same direction, even if the AC input swings in the other direction. So what does this produce? An ongoing positive pulse across the load, just like in the half wave rectification, except you'll get another one during the negative half cycle because we utilize both cycles in a full wave rectifier. Hey listeners, we're now in the second half of the bridge full wave rectifier story following the current during the negative half cycle of the AC input. So what changes? Now that the AC input swings negative, the top terminal of the transformer is negative and the bottom terminal is positive. This reverses the polarity across the input, but thanks to the bridge configuration, the output stays flowing in the same direction. So here's going to be the new path. D3 and D4 are now forward biased, so those are conducting, where D1 and D2 are reverse biased, so those are shut off. So current is going to flow from the positive terminal of the AC source through D3 into the load resistor, R sub L, out through D4, and then back to the negative terminal. And the result's going to be that the load sees another positive pulse, just like during the previous half cycle. And the magic of the bridge is that every half cycle of AC, it flips and it's funneled through the load in the same direction because of the way the circuit is designed. And so this ends up doubling the ripple frequency and maximizing power output. The key takeaways here are that in the positive half, diodes D1 and D2 conduct. In the negative half, diodes D3 and D4 take over, but the load current direction never changes. Okay, let's go ahead and do the same exercise with a slightly different looking circuit, but trust me, it's the same one. So before we follow current through a bridge rectifier using the positive half cycle, let's flip the input and walk through the negative half cycle where different diodes, right, take charge, but the output, again, is going in the same direction. So input polarity reverses from the top terminal to the bottom terminal. So now the top terminal is negative, the bottom terminal is positive. This reverses the voltage at the input, but the bridge circuit, again, is still built the same way. So that flip to the power doesn't cause any change in the direction of current flow. So again, repeating what we said in the last slide, which diodes turn on? D3 and D4 are on, D1 and D2 are off, right? Current path, I'm just repeating from the last slide, is from the positive terminal, so bottom of the source, through D3, across the load resistor from top to bottom, through D4, and back to the negative terminal of the source. What does the load end up seeing? So it just sees another positive voltage pulse, just like the previous half cycle. So the previous half cycle, it saw a positive going pulse. On the next cycle, the negative cycle, the output is still another positive going voltage pulse. Right? So every half cycle gets converted into forward current. Output frequency is doubled, that of the input frequency, and current always flows in the same direction through the load. Seeing how the bridge full wave rectifier works during both half cycles, let's look at the numbers now, or some numbers. The output voltage and the peak inverse voltage rating that you need to watch out for. So the peak output voltage, so when current flows through the bridge, it always passes through two diodes, one on the top half of the loop and one on the bottom. So each of these are forward bias silicon diodes, and each of these drops 0.7 volts. So the whole KVL, the total voltage drop, is going to be equal to 1.4 volts, since we're adding the voltage drops. So the output equation becomes V sub out is going to be equal to VP in the secondary minus 1.4 volts. So if we want to plug in some numbers, if the secondary peak voltage is, say, 20 volts, VP out is going to be 20 volts minus 1.4 volts, which is going to be 18.6 volts. And that would be the peak output voltage. Now the peak inverse voltage, remember, even though two diodes conduct per cycle, the non-conducting diodes still have to withstand the full reverse voltage. So peak inverse voltage is going to be voltage peak out plus 0.7 volts. So the extra 0.7 here accounts for the forward bias diode that shares the load path. So the rule of thumb would be, again, now that we're looking for a rating for this particular inverse voltage, we can choose a diode, again, rated at 20 to 25% higher than the calculated PIV. So in this case, VP out is going to be equal to VP from the secondary minus 1.4 volts. And the peak inverse voltage will be VP out plus 0.7 volts. And so always account for the double diode drop in the bridge designs. Okay, we've covered bridge rectifiers in theory. Now let's work through some real examples using actual transformer values. So let's go ahead and set this up. If we give you a primary voltage of 120 volts, that's standard what comes from the wall supply, and a secondary voltage of 12 volts RMS, and you're asked to find the peak output voltage and the peak inverse voltage rating for the diodes in a bridge rectifier, right? The first step would be to convert RMS to peak. That's one of the things, so we can keep everything in the same units. If you're using peak voltage on the input, use peak voltage in the output. So that's going to be voltage peak of the secondary. It's going to be equal to VRMS times the square root of 2. So that's, in this case, 12 volts times 1.414. And that gives us 16.97 volts for voltage peak on the secondary. The next thing we want to do in step 2 is apply the double diode drop. Right? So I know that's alliteration, but I didn't mean for it to be the double diode drop. That sounds pretty cool. So since a bridge rectifier uses, again, 2 diodes per cycle, we're dropping 0.7 across each. So that adds up to 1.4 volts total. So VP out is going to be VP of the secondary minus 1.4 volts. So we already said the VP of the secondary, when we converted from RMS to peak, was 16.97 volts. You subtract 1.4 volts from that, and we end up with a voltage on the output of 15.57 volts. All right. The next thing we want to do is calculate the peak inverse voltage rating. So remember that PIV is going to be equal to VP out plus that 0.7 volts. And so we add the 15.57 plus 0.7 volts. That's going to give us a peak inverse voltage of 16.27 volts. And that's it. The peak output voltage was 15.6. The minimum peak inverse voltage rating was 16.3. It was 16.27. And then again, you want to make sure that you choose a component that's greater than 20% above that peak inverse voltage. So 1.2 times 16.3, and pick a voltage that's at least that high. Okay, so you've converted your AC to DC with a full wave rectifier, but there's still one problem, right? And that's called a ripple. That's the bumpy output that won't work for sensitive electronics. So now it's time to bring in another hero of our power supply, and that's the filters. And that's the way filters are something that we use to clean the power supplies. So it's a circuit. It's added after the rectifier, and what its job is to smooth out voltage fluctuations. It tends to flatten the bumps to create a more constant level looking DC. You'll still have some ripple, but it'll be a whole lot smaller than what you started off with. And so you're asking what causes ripple? Well, after you rectify the sinusoidal waveform, you get a waveform that's pulsed. So if you remember from the previous slide, just bunch of little hills going up and down on the positive side. It's unidirectional, means so we're only going on the positive side, and it's full of those ups and downs, and we call those ups and downs ripples. So if it starts from 0, goes all the way to some peak, goes all the way back down to 0, and then goes back up to some peak, goes back down to 0. That's like the maximum ripple you can get because starting from zero going to some peak. Um, and we use filters to smooth this out. So what happens is it stores energy during high points and then releases it slowly during the low points to fill in the gaps. So what that ends up doing when we add a filter is that once the waveform goes to its peak and the input starts going down, some of it that was actually stored in the network, in the RC, in this case, let's say an RC network filter, that also starts discharging as the input goes down. So the input never goes all the way back down to zero, or at least the output doesn't go back down to zero because as the input's going down, um, the voltage, the energy that was stored in the filter gets released. So it keeps it from going all the way down to zero. And so the better filters have like smaller ripples up on top and they don't go that far down, not back down to zero. And that's it. We can make LC filters and RC filters. Just depend on where you physically set up the components. Um, that that's it for this slide. Okay, now we're adding the first layer of smoothing to our rectified signal using the classic combo, a half-wave rectifier with a capacitive filter. So with this, you've got a simple half-wave rectifier, you got an AC source, a single diode, and a load resistor. So let's go ahead and add a capacitor across the load to kind of tame that ripple. What happens during the first quarter cycle, when the input voltage starts rising, the diode becomes forward biased. The capacitor charges up quickly through the diode, and it charges to voltage peak input minus the zero point 0.7 volts because the diode drops, remember, 0.7 volts when it's conducting. On the graph, you'll see the capacitor voltage rise right up to the peak of the AC wave, minus that little diode drop. And after that peak, the input drops, but the capacitor holds onto that charge. So then what happens? Once the input voltage drops below the capacitor voltage, the diode turns off, and the capacitor now acts like a temporary battery feeding the load. And this works because the capacitors fill in those gaps between those half-wave pulses. It creates a smoother, more stable DC output. It doesn't allow it to get back down to zero, if you can remember what they looked like before. And now it just kind of goes down to some value and comes right back up on the next cycle. So what's going to happen is you're going to have less ripple, you're going to have better voltage regulation, and this will be a good first step toward having a clean DC signal for your sensitive electronics. Okay, in the last slide, the capacitor in our half-wave rectifier charged up to the peak voltage minus the diode drop. But what happens when the input voltage starts to fall again? So we're going to explore that discharge phase in a little more detail. This is where the capacitor takes over. So what happens after the peak? So as the AC waveform drops below the capacitor voltage, the diode becomes reverse bias. It turns off. This prevents the capacitor from discharging back into the source, and the capacitor now powers the load directly. So the capacitor discharge begins. And once the capacitor starts discharging through the load resistor and the voltage begins to decay gradually, that decay ends up shaping the waveform to what you see there on the slide. And that's determined by the RC time constant. If you remember that, how long it takes for a resistor and a capacitor circuit to actually charge and discharge. Right? So that's not going away. So the time constant rule of thumb is that larger RLs, the load resistors, and or larger capacitors equals slower discharge, so you'll have smoother outputs. If you have smaller values for R and C, you're going to have faster drops and you're going to have more ripple. But on the graph, the voltage holds near the peak briefly, then it starts sloping downwards until the next AC pulse arrives, and then the dial turns back on, recharges the capacitor, and this cycle repeats over and over again. And you get a series of rounded voltage pulses, but they'll be much smoother than the original ripple, so they won't be as pointy, in other words. Um, Especially if you got an RC constant that you chose well. So we're wrapping up the behavior of a half-wave rectifier with a capacitive filter, this time focusing on the time constant and how the capacitor recharges with each cycle. So let's go ahead and revisit the RC time constant theme, right? The discharge rate of the capacitor depends on its load resistor and its capacitance. That's how we get tau, which is the equation for a time constant. Remember that the larger this time constant, the slower the capacitor discharges. And the result's going to be a flatter, more stable DC output. If tau is too small, if that time constant is too small, the capacitor empties too quickly and the ripple just increases. What happens in the next AC cycle? So as the next input wave starts rising, the diode stays off until the input voltage is greater than the capacitor voltage. So once the threshold is passed, the diode turns on and the capacitor recharges, and this restores voltage lost during the discharge period. On a graph, you'll see a sawtooth like a ripple. So it charge, discharge, repeat, charge, discharge, repeat. And the goal for this in design is to make sure that your time constant exceeds the period of the AC signal so that the capacitor holds voltage long enough between charges. What I mean by that is keeping that time constant as long as possible before the next cycle starts. That way, you'll have some overlap and you'll get a smoother DC output. So some tips: bigger capacitor equals for better smoothing. High load resistance equals for slower discharging. And together with these two, big capacitor, big resistance, they'll help reduce the ripple. Okay, you've learned how filters reduce ripple in rectified circuits, and now it's time to put that theory to the test in a simulation. So let's look at this first. Which circuit has less ripple voltage? You have two circuits here and one key difference. So both circuits are identical in that the source voltage is 5 volts peak. They're using a frequency of 2 kilohertz. They're using a diode of a 1N 4001G and a capacitor of 1000 microfarads. So what's the difference? The left circuit has a load resistor of 500 and the right circuit has a load resistor of 2K or 2000. So if we compare the discharge behavior, remember that RC time constant is a tau. So tau is equal to R sub L times C, right? So if you have a large R, a large time constant, this means the capacitor discharges slower and you'll have less ripple. So large R, large resistance, less ripple. So the left circuit, tau, is going to be 500 times 1000 microfarads, which is going to equal to 0.5 seconds. That's the time constant. The right circuit, tau, is equal to 2000 times 1000 microfarads. And so that's going to be equal to 2 seconds for the first time constant. Um, so on the conclusion, we can look at this and say the right side circuit with 2000 ohms with that load, that's going to have less ripple voltage because the capacitor holds its charge longer between charges. So taking 2 seconds is quite a long time. Okay, you've added filter capacitors, you've controlled the charge and discharge, but what you're still seeing on the output isn't perfectly flat. So there's some variation, and again, we call that variation ripple voltage. We're still trying to minimize that ripple voltage. So we talked about before, as the capacitor charges and discharges between each rectified pulse, the output voltage isn't constant, right? It rises, it dips, it rises again, and this back and forth motion, again, we call it the ripple voltage. This matters because too much ripple can cause unstable power. Digital circuits can misfire. Audio amps may develop a hum, and you may have some glitches if you have any sensors, because those need some steady current. So the goal is to have the smallest ripple as possible that will equal better filtering. So smaller ripple, better filtering. So let's talk about the load resistance first. So take a look at this comparison. So on the left graph, you have a higher RL, load resistor, and the capacitor discharges slowly, and so the ripple is small. That's good filtering. On the right graph, we have a lower RL, so the capacitor discharges quickly. So in this case, the ripple is larger, so you have weaker filtering. And why is this? Well, because the time constant, if you can remember that, tau is equal to R times C, RC time constant. So R times C, so if you have a high load resistor, that means you're going to have a longer discharge time. The capacitor holds its voltage better between peaks. And that's it. Some tips for this circuit is that if you increase C, meaning a larger capacitor, that'll give you less ripple. If you increase RL, That means you're going to have less current draw, so it's also going to help you have less ripple. You can also add a second stage filter if you need it. But that's it. Hey, listeners, you've learned the ins and outs of halfway and full wave rectifiers, but how do they stack up when it comes to performance? So today we're breaking down half wave versus full wave in frequency, filtering, and ripple. So let's go ahead and compare the two. So for the first thing we want to look at is the output frequency. So a half wave rectifier output is once per AC cycle. So the same input frequency, the output frequency is the same as the input frequency. But on a full wave rectifier, the output is twice per cycle. That means that this doubles the frequency of the output. So this means that full wave rectifiers have shorter time gaps between charging pulses. They're easier to filter and they have smoother DC output. Now the next spec that we want to look at is ripple voltage. So half wave ripple voltage on half wave rectifiers is long time between pulses. You have more capacitor discharge, you have bigger ripple. When you're dealing with a full wave, you have shorter gaps, less voltage drop between pulses, and you have a smaller ripple. You can use multisim and demonstrate to see how this works, right? So if you had a circuit, the left half here, the half wave with the 1.16 volt DC and the 773 microamps for I sub P, that will lower the overall performance. On the right side there in that yellow box, we have a 2.31 volts DC at 401 microamps for the ripple. That's cleaner and that's stronger, a stronger output, right? All right, listeners, we've been talking about ripple and smoothing your DC output, but how do you actually measure how effective you're filtering? We're going to introduce the ripple factor and some key performance metrics for power supply quality. So this again, rehash what the ripple factor is, or what is the ripple factor. And ripple factor is denoted by R. That just tells you how much ripple remains in the output compared to the average DC level. And it's defined by the formula um, ripple factor R is going to be equal to V sub R, peak to peak, divided by VDC. So V sub R, peak to peak ripple voltage, and VDC is the average DC output after it's filtered. So if you have like a low R, that means you're going to have better filtering. A perfect filter would give you R is equal to 0. So real world filters aim to keep the ripple as small as possible, often less than about, say, 10%, even down to 1% if possible or when possible. Um, but how do we calculate ripple voltage? This is important. So we get a rectified filter signal. We can estimate the ripple voltage by using the formula VR PP, which is the ripple voltage, is equal to 1 divided by frequency times resistance times inductance times capacitance, all of that times the voltage peak rectified. Okay. So F is going to be the frequency of the rectified signal. R sub L is the load resistance, C is capacitance, and VP is the rectified voltage, the peak value before filtering. So calculating the resulting DC voltage, we end up with the formula VDC is equal to 1 minus 1 over 2 FRLC times all of that times VP rectified. And this is going to give you a sense of how much the output dips under load. You're asking, well, why does this matter? Well, because ripple factor helps you out. You have to compare filter designs, and this is one thing to look at. You can select proper capacitor values based on your designs, and you can create tuned RC constants to hit your desired performance. Okay, by now we've shaped, rectified, and filtered AC into smooth DC, but there's one last piece to guarantee clean, consistent voltage for your circuits, and that is the voltage regulator component. So what does the voltage regulator do? I know we're calling this whole thing a voltage regulator, but this is a component, right? It's your power supply's final defense. It ensures that the output voltage stays constant no matter what happens, right? So this is our last check, quality check, as far as components and design is concerned. So no matter what happens to the input voltage, the load current, even if temperature fluctuates, it's going to take that bumpy ripple voltage, that imperfect DC, and it's going to lock it into a DC voltage. So most regulators are 3-terminal ICs, like, and some of the popular ones are the 7805. That's a 5-volt regulator, voltage regulator. The 7905, that's a negative 5-volt voltage regulator. So a quick, um, you know, understanding of the numbering systems for voltage regulators, because they're written very straightforward and easy. If it has a 78, if it starts with 78, that's going to be a positive voltage regulator. If it has a 79, that's going to be a negative voltage generator. So if I say 7805, so that's a positive 5-volt voltage regulator. If I have a 7905, that's a negative 5-volt voltage regulator. So let's say I was looking for a negative 15-volt voltage regulator. So negative would tell me it's in the 7900 series. And since I'm trying to regulate 15 volts, negative 15 volts, the second two numbers will be 15. So 7915 for a negative 15 voltage, negative 15 volt regulator. All right. So yeah, those are some common ones, and that's the numbering system. So what you need to do is you'll connect the input voltage, you'll connect the ground pin, and then you get your regulated output out of the output pin. The chips, they'll use internal circuitry to compare, they'll trim, they'll stabilize the voltage in real time. So this is being done through hardware. It's also good to pair this with the capacitor. Again, remember capacitors, they'll charge and discharge, so they'll do it at a certain time constant, and that's going to help actually filter the output. So that's going to give us filtering, ripple reduction, and some transient response, some better transient response. So a quick tip, if we're looking at the voltage regulator that you see there, C1 before the regulator and C2 is after the regulator. Um, what do we need to know? That's it. Just so we got one before and one after. It keeps microcontrollers and ICs safe. So IC just integrated circuit. It prevents resets. It prevents noise and brownouts, and it boosts the reliability of the entire project. Okay. But the voltage regulator alone will do a great job. With the extra capacitors, you'll get an even better, smoother output. Okay, you've installed your voltage regulator, but how do you make sure it stays stable and responsive across different conditions? We're going to be dialing it in today or right now with the capacitor use, and we're going to look at two key aspects. One is called the line regulation, and the other thing is called load regulation. Again, if you work in facilities management, where you're supplying power to a building, this will be kind of important for you. If you design power supplies, again, this will also be very important for you. But let's go and start off with the capacitors. Right? So even the best regulators need some support. So you want to use a large input capacitor, especially if your supply is noisy or it's unstable. On the output, you want to add something like a zero point 0.1 microfarad or a 1.0 microfarad capacitor. Close that to ground, and this filters out transient spikes and helps keep your voltage steady. So looking at the voltage regulators themselves, the components, right? Most of these IC regulators, like the 7805, the 7812, and the other ones, which are like the LM317, they're going to have 3 pins, an input, a ground, and an output. And they're designed to produce fixed DC voltages, and they're super easy to use. All you got to do is just, wire them up, and they're designed to work at a certain voltage. But you got to understand a little bit more about the specs before you start using them. So let's talk about line regulation. How well does the regulator handle fluctuations in input voltage? So if the input jumps, let's say from 12 volts to 14 volts, does the output stay at 5 volts? Good regulators are going to keep the output stable within millivolts of change. So you use this when you have variable or poorly filtered power upstream. The next thing I want to talk about is load regulation. So how much does the output voltage change with different current demands? So from 0 milliamps to 500 milliamps, does the voltage sag or spike? And this specification tells you how tight the output stays under load. So when I say tight load regulation, that just means better performance for things like microprocessors, microcontrollers, sensors, and other things like that. So to recap on this slide, use capacitors to smooth the ripple and spikes. Know your line regulation to survive noisy inputs, and watch the load regulation to power devices consistently. And that's it for this second podcast. I will see you on the next one.